Today we will learn Atterberg limits tests. Introduction. As we know, fine-grained soils such as clay and plastic shells have a relatively large specific surface and therefore surface force dominate in their characteristics. A fine-grained soil can exist in any several states, which state depends on the amount of water in the soil system. When water is added to such dry soil, each particle is covered with a film of absorbed water. If the addition of water is continued, the thickness of the water film on a particle increases. Increasing the thickness of the water films permits the particle to slide past one another more easily. The behavior of the soil, therefore, is related to the amount of water in the system. In the early 90s, Swedish soil scientist A. Atterberg identified different states in cohesive soil depending on the amount of water in the system. He was working in the ceramic industry, and at that time they had several simple tests to describe the plasticity of the clay, which was important both in molding clay into bricks, for example, and to avoid shrinkage and cracking when fired. After many experiments, Atterberg came to the realization that at least two parameters were required to define plasticity of clays: the upper and lower limits of plasticity. He was able to define several limits of consistency or behavior, and he developed simple laboratory tests to define these limits. They are: upper limit of viscous flow, liquid limit, lower limit of viscous flow, sticky limit, clay loses its adhesion to a metal blade, cohesion limit, grains cease to cohere to each other, plastic limit, lower limit of the plastic state, shrinkage limits, lower limit of the volume change. He also defined the plasticity index, which is a range of water content where the soil is plastic, and he was the first to suggest that it could be used for soil classification. Later on, in the late 1920s, Tazagi and A. Casagrande 1932b, working for the U.S. Bureau of Public Roads, standardized the Atterberg limits so that they could be readily used for soil classification purposes. In present geotechnical engineering practice, we usually use the liquid limit LL or WL, the plastic limit PL or WP, and sometimes the shrinkage limit SL or WS. The sticky and the cohesion limits are more useful in ceramics and agriculture. Since the Atterberg limits are water contents where the soil behavior changes from one phase to another phase, we can show these limits on a water content continuum. Also shown are the types of soil behavior for given ranges of water contents. As the water content increases, the state of the soil changes from a brittle solid to a plastic solid and then to a viscous liquid. Atterberg's original consistency limit tests were rather arbitrary and not easily reproducible, especially by inexperienced operators. As mentioned, Casagrande 1932b 1958 worked to standardize the test, and he developed the liquid limit device figure 3.2 so that the test became more operator independent. He defined the LL as that water content at which a standard groove cut in the remolded soil sample by a grooving tool, figure 3.2a-b, will close over a distance of 13 mm 1 by 2 inch at 25 blows of the LL curve falling 10 mm on a hard rubber or micarta plastic base, figure 3.2c. In practice, it is difficult to mix the soil so that the groove closure occurs at exactly 25 blows, but the Casagrande found that if you plot the water contents of test where you get closer at other blow counts versus the logarithm of the number of blows, you get a straight line called the flow curve. Where the flow curve crosses 25 blows, that water content is defined as the liquid limit. The plastic limit test is somewhat more arbitrary. and it requires some practice to get consistent and reproducible results. The PL is defined as the water content at which a thread of soil just crumbles when it is carefully rolled out to a diameter of 3 mm. It should break up into segments about 3 to 10 mm long. If the threads can be rolled to a smaller diameter, then the soil is too wet above the PL. If it crumbles before you reach 3 mm in diameter, then you are past the PL. The limits are determined on the portion of soil finer than has 40 sieve. Shrinkage limit SL is defined as the moisture content at which no further volume change occurs with further reduction in moisture content. SL represents the amount of water required to fully saturate the soil, 100% saturation. It is needed in producing bricks and ceramics. Scope of the test. This test is performed to determine the plastic and liquid limits of fine-grained soils. Significance. The Swedish soil scientist Albert Atterberg originally defined 7 limits of consistency to classify fine-grained soils, but in current engineering practice, only 2 of the limits, the liquid and plastic limits, are commonly used. A third limit, called the shrinkage limit, is used occasionally. The Atterberg limits are based on the moisture content of the soil. The plastic limit is the moisture content that defines where the soil changes from a semi-solid to a plastic flexible state. The liquid limit is the moisture content that defines where the soil changes from a plastic to a viscous fluid state. The shrinkage limit is the moisture content that defines where the soil volume will not reduce further if the moisture content is reduced. A wide variety of soil engineering properties have been correlated to the liquid and plastic limits, and these Atterberg limits are also used to classify a fine-grained soil according to the Unified Soil Classification System or ASTHO system. Equipment: liquid limit device, porcelain evaporating dish, flat grooving tool with case, moisture cans, balance, glass plate, spatula, wash bottle filled with distilled water, drying oven set at 105 degrees C. Test procedure. Liquid limit. 1. Take roughly 3 by 4 of the soil and place it into the porcelain dish. Assume that the soil was previously passed through a number 40 sieve, air dried and then pulverized. Thoroughly mix the soil with a small amount of distilled water until it appears as a smooth uniform paste. Cover the dish with cellophane to prevent moisture from escaping. 2. Weigh 4 of the empty moisture cans with their lids and record the respective weights and can numbers on the data sheet. 3. Adjust the liquid limit apparatus by checking the height of drop of the cup. The point on the cup that comes in contact with the base should rise to a height of 10 mm. The block on the end of the grooving tool is 10 mm high and should be used as a gauge. Practice using the cup and determine the correct rate to rotate the crank so that the cup drops approximately 2 times per second. 4. Place a portion of the previously mixed soil into the cup of the liquid limit apparatus at the point where the cup rests on the base. Squeeze the soil down to eliminate air pockets and spread it into the cup at a depth of about 10 mm at its deepest point. The soil pad should form an approximately horizontal surface. 5. Use the grooving tool carefully. Cut a clean straight groove down the center of the cup. The tool should remain perpendicular to the surface of the cup as groove is being made. Use extreme care to prevent sliding the soil relative to the surface of the cup. 6. Make sure that the base of the apparatus below the cup and the underside of the cup is clean of the soil. Turn the crank of the apparatus at a rate of approximately 2 drops per second and count the number of drops it takes to make the two halves of the soil pad come into contact at the bottom of the groove along a distance of 13 mm 1 by 2 inch. If the number of drops exceed 50, Then go directly to step 8 and do not record the number of drops, otherwise record the number of drops on the dataset. 7. Take a sample using the spatula from edge to edge of the swell pad. The sample should include the swell on both sides of where the groove came into contact. Place the swell into a moisture can, cover it. Immediately weigh the moisture can containing the swell, record its mass, remove the lid and place the can into the oven. Leave the moisture can in the oven for at least 16 hours. Place the swell remaining in the cup into the porcelain dish. Clean and dry the cup on the apparatus and the grooving tool. 8. Remix the entire swell specimen in the porcelain dish. Add a small amount of distilled water to increase the water content so that the number of drops required closing the groove decreases. 9. Repeat steps 6, 7 and 8 for at least 2 additional trials, producing successively lower number of drops to close the groove. One of the trials shall be for a closure requiring 25 to 35 drops, one for closure between 20 and 30 drops, and one trial for closure requiring 15 to 25 drops. Determine the water content from each trial by using the same method used in first laboratory. Remember to use the same balance for all weighing. Plastic limit. 1. Weigh the remaining empty moisture cans with their lids and record the respective weights and can numbers on datasheet. 2. Take the remaining 1/4 of the original swell sample and add distilled water until the swell is at a consistency where it can be rolled without striking to the hands. 3. Form the swell into an ellipsoidal mass. Roll the mass between the palm or the fingers and the glass plate. Use sufficient pressure to roll the mass into a thread of uniform diameter by using about 90 strokes per minute. A stroke is one complete motion of the hand forward and back to the starting position. The thread shall be deformed so that its diameter reaches 3.2 mm, 1/8 inch, taking no more than 2 minutes. 4. When the diameter of the thread reaches the correct diameter, break the thread into several pieces. Knead and reform the pieces into ellipsoidal masses and re-roll them. Continue this alternate rolling, gathering together, kneading and re-rolling until the thread crumbles under the pressure required for rolling and can no longer be rolled into a 3.2 mm diameter thread. 5. Gather the portion of the crumbled thread together and place the swell into moisture can and then cover it. If the can does not contain at least 6 grams of swell, add swell to the can from the next trial. Immediately weigh the moisture can containing the swell, record its mass, remove the lid and place the can into the oven. Leave the moisture can in the oven for at least 16 hours. 6. Repeat steps 3, 4 and 5 at least 2 more times. Determine the water content from each trial by using the same method used in the first laboratory. Remember to use the same balance for all weighing. Shrinkage limit determination. Procedure in brief. 1. A sample of fine-grained swell is thoroughly remolded with water to approximate the liquid limit consistency. 2. The saturated paste is placed into a container of known volume and slowly dried. 3. The final mass and volume of the solid swell pad are determined. 4. These measurements are used to compute the SL. Procedure in detail. Volume of wet swell pad. 1. Make the swell paste of liquid consistency. 2. Coat the inside of the shrinkage dish with a thin layer of petroleum jelly, silicone grease or similar lubricant to prevent the adhesion of the swell to the dish. 3. Determine and record the mass in grams of the empty dish empty. 4. Place the shrinkage dish in the shallow pan in order to catch any mercury overflow. 5. Fill the shrinkage dish to overflowing with mercury. 6. Remove the excess mercury by pressing the glass plate firmly over the top of the shrinkage dish. 7. Determine the volume of mercury held in the shrinkage dish either by means of the glass graduate or by dividing the measured mass of mercury by the mass density of mercury equal to 13.55 mg per m cube. 8. Record this volume in cubic centimeters of the wet soil pad B. Procedure in detail. Volume of dry soil pad. 1. Place the glass cup in the shallow pan in order to catch any mercury overflow. 2. Fill the glass cup to overflowing with mercury. 3. Remove the excess mercury by pressing the glass plate with the three prongs firmly over the top of the cup. 4. Place the evaporating dish in the shallow pan in order to catch any mercury overflow. Place the cup filled with mercury in the evaporating dish and rest the soil pad on the surface of the mercury. It will float. 5. Using the glass plate with the three prongs, gently press the pad under the mercury and press the plate firmly over the top of the cup to expel any excess mercury. Observe that there is no air trapped between the plate and mercury. 6. Measure the volume of the mercury displaced into the evaporating dish either by means of glass graduate or by dividing the measured mass of mercury by the mass density of mercury. 7. Record the volume in cubic centimeters of the dry soil pad V0. Analysis to determine liquid limit. 1. Calculate the water content of each of the liquid limit moisture cans after they have been in the oven for at least 16 hours. 2. Plot the number of drops in on the log scale versus the water content W. Draw the best fit straight line through the plotted points and determine the liquid limit LL as the water content at 25 drops. Analysis to determine plastic limit. 1. Calculate the water content of each of plastic limit moisture cans after they have been in the oven for at least 16 hours. 2. Compute the average of water contents to determine the plastic limit PL. Check to see if the difference between the water contents is greater than the acceptable range of two results, 2.6%. 3. Calculate the plasticity index PI is equal to LL minus PL. Report the liquid limit, plastic limit and plasticity index to the nearest whole number, omitting the percent designation. Analysis to determine shrinkage limit. 1. Calculate the water content of each of the liquid limit moisture cans after they have been in the oven for at least 16 hours. W is equal to M minus M naught divided by M naught into 100. 2. Compute shrinkage limit by the following equation. SL is equal to W minus V naught rho W divided by M naught into 100. Figure 7.4. A. Grind the soil sample into pieces. B. Mix considerable amount of water with the soil and make a paste. C. Using the spatula, place soil sample to the liquid limit device. Cut the soil sample using grooving tools and give anti-clockwise blow. D. After come in contact the soil, take samples, wet and dry them. Figure 7.5. A. Ellipsoidal soil mass. B. Soil rolling. C. Soil gets crumbled at 1/8 inch.